Hi, and welcome back. This is our section about optimization, which in this context refers to the algorithms we will use to vary our model's parameters. So far, we've seen the gradient descent only, and now it is time to discuss improvements that will lead to enhanced algorithms. Most of what we have learned is invaluable from a theoretical viewpoint, but slow when it comes to practical execution. However, there are simple steps to take to turn things around. Let's start with the clumsiest optimizer, the gradient descent. The GD, short for gradient descent, iterates over the whole training set before updating the weights. Each update is very small. That's due to the whole concept of the gradient descent, driven by the small value of the learning rate. As you remember, we couldn't choose a value too high, as this jeopardizes the algorithm. Therefore, we have many epochs, over many points, using a very small learning rate. This is slow. It's not descending, it's basically snailing down the gradient. Fortunately for us, there is a simple solution to the problem. It's a similar algorithm called the SGD, or the stochastic gradient descent. It works in the exact same way, but instead of updating the weights once per epoch, it updates them in real time inside a single epoch. Let's elaborate on that. The stochastic gradient descent is closely related to the concept of batching. Batching is the process of splitting data into n batches, often called mini batches. We update the weights after every batch, instead of every epoch. Let's say we have 10,000 training points. If we choose a batch size of 1,000, then we have 10 batches per epoch. So, for every full iteration over the training data set, we would update the weights 10 times instead of 1. This is by no means a new method. It is the same as the gradient descent, but much faster. As all good things go, the SGD comes at a cost. It approximates things a bit. So, we lose a bit of accuracy, but the trade-off is worth it. That's confirmed by the fact that virtually everyone in the industry uses stochastic gradient descent, not gradient descent. So, why does this speed up the algorithm so drastically? Was it worth talking about it for 3 minutes? There are a couple of reasons, but one of the finest is related to hardware. Splitting the training set into batches allows the CPU cores or the GPU cores to train on different batches in parallel. This gives an incredible speed boost, which is why practitioners rely on it. Okay, one last thing. Actually, stochastic gradient descent is when you update after every input, so your batch size is 1. What we have been talking about was technically called mini batch gradient descent. However, more often than not, practitioners refer to the mini batch GD as stochastic gradient descent. If you are wondering, the plain gradient descent we talked about at the beginning of the course is called batch GD, as it has a single batch. Okay, perfect. Now we can confidently close this topic. Thanks for watching.